So hello and welcome everyone. Greetings from the Australian National University. I hope that you and your loved ones, wherever you're joining us today from, are keeping safe and healthy. My name is Jay and I look after international relations and partnerships here at the ANU in the areas of sciences, health and medicine. I'm joined today by my colleague Arthur Xu and of course our speaker for today, Professor Mark Krumholz. Before we start, I would like to acknowledge the Ngunnawal and Ngambri people who are the traditional owners of the land where ANU is located and where we are broadcasting to you today from, and I pay my respects to their elders past and present. Now, let me very quickly introduce our speaker for today, Professor Mark Krumholz. Mark is a professor of theoretical and computational astrophysics at the ANU Research School of Astronomy and Astrophysics, which is located at the historic and well-known Mount Stromlo Observatory here in Canberra. His research focuses on the formation of stars and galaxies, on the physics of the interstellar medium, and numerical and statistical methods for astrophysical simulation and data analysis. After receiving his PhD from University of California, Berkeley in 2005, Mark spent time researching and teaching at Princeton University and University of California in Santa Cruz before joining the ANU as a professor in 2015. There is a stellar list, no pun intended, of awards and fellowships that Mark has received for his unique research contributions. These include the National Science Foundation Career Award, the Humboldt Research Award from the Alexander von Humboldt Foundation, the Helen B. Warner Prize from the American Astronomical Society, the Anne Green Prize from the Astronomical Society of Australia, a future fellowship from the Australian Research Council, and many, many more. We're lucky to have Mark give us a talk today, and I'm sure you're all as excited as me to know more about one of the oldest problems in theoretical astrophysics. Look, without any further delay, I'll now hand over to Professor Mark Krumholz to give his talk. Over to you, Mark. I'll stop sharing.
Thank you for that introduction, and thank you for using the photo of me when I was 10 years younger than I am now. It is the same person despite appearances. So let me put up my slides here. All right, so as I mentioned, I will try and keep track of questions in real time. So if I say something that's unclear, feel free to ask. I'm going to try and tell you something about what sets the masses of stars, which is, as Jay mentioned, a really old question in astrophysics. Why do stars have the masses they do? So before I dive into the talk, here's the outline. So I'm going to start by sort of telling you about, well, first of all, what do we mean by the masses of stars? I'll introduce this thing called the IMF, and I'll talk about what we observe. And then I'll talk about trying to understand where this thing comes from, the origin of the IMF. And I'll end with some open questions, things that we don't really understand the answer to yet. So let's start with part one. What is the IMF? You might think the International Monetary Fund. No. By the way, I of course cannot see or hear anyone's reaction, so I'm going to assume that you will all think my jokes are hilarious because it would be really depressing for me to think otherwise. So I'm just going to assume you're laughing at my jokes as I go. All right, so what is the IMF? All right, it's not the International Monetary Fund. The IMF is this thing called the initial mass function. So what does that mean? So the IMF is the distribution of the masses of stars at birth, meaning before stars change their masses at all because they're losing mass via stellar winds or exploding as a supernova or anything like that. So what you can imagine is, suppose that I take a bunch of stars that have just formed and I just count how many stars are there between 1 times the mass of the sun and 2 times the mass of the sun. How many between 2 times the mass of the sun and 3 times the mass of the sun? 3 and 4, 4 and 5. And I just make a little histogram of how many are in each mass bin. That's all the IMF is. It's just a count of how many stars there are in each bin of mass. Now, observationally, if I want to actually measure this, well, for low mass stars, things the size of the sun, that little funny symbol you may see on your screen, that it means the mass of the sun. For things that are the mass of the sun or less, then the initial mass is nearly identical to the present day mass because stars the size of our sun or smaller don't lose much mass over the course of their lifetimes. On the other hand, if we're talking about things more than, say, 10 times the mass of the sun, we have to measure the initial mass function when the star is very young, because things that are 10 times the mass of the sun will blow up as supernovae and lose almost all of their mass within a few million or tens of millions of years after they form. So that's what we mean by at birth or young. So why are we interested in IMF? Why does it matter? Well, I mean, partly we're interested in just stars and understanding them, but it matters a lot for lots of other things too, because stars are the nuclear reactors that are the engines of the universe. And what I mean by that is that if you look at all the light that exists in the universe, the majority of it is starlight. Most light that we see was made by nuclear reactions inside stars. Stars and their supernova explosions are the dominant source of energy that regulates the formation of galaxies. If you want to understand how galaxies form, the central thing that happens is that stars form and then the most massive of them blow up in supernova explosions. And that's the dominant thing that controls how galaxies form. Stars produce almost all of the heavy elements, all of the chemical elements heavier than hydrogen and helium. All right, so the stuff we're made of was all made in stars. And of course, stars determine where life can evolve. As far as we know, life requires a certain range of temperatures, and that range of temperatures is really found in certain zones around stars. So stars do all of this. Now, the reason we care about the IMF is because stars do all this because they're nuclear reactors, but stars of different masses are very, very different sorts of nuclear reactors. So a 100 solar mass star, a star 100 times the mass of the sun, will burn about 0.5% of its initial mass into light. That's what nuclear reactors do. They convert mass to radiation. So a star 100 times the mass of the sun will turn about 0.5% of its initial mass into light over a span of 3 or 4 million years. That's a very efficient, fast-burning reactor. On the other hand, a star like our sun will convert about 0.1% of its initial mass into light, but instead of doing it in a few million years, it will require about 10 billion years to accomplish this task. So even though it has 10 billion years, it will still only turn a smaller percentage of its mass into light. So because stars are the nuclear reactors of the universe that do all of these things, and because stars of different masses are very different sorts of nuclear reactors, we care a lot about how many stars there are of different masses. A universe where the typical star is 100 times the mass of the sun looks very, very different than a universe where the sun is typical, looks very, very different than a universe where something the mass of Jupiter is typical. So that's why we care about the IMF. What does it actually look like? Well, if we want to measure the IMF for stars about the mass of the sun or smaller, we can do that very straightforwardly just by counting stars in the solar neighborhood. And the reason is, as I mentioned, these stars don't change their masses over time. All of the ones that have formed are still alive. And so you can simply look around the sun and count how many stars there are of different masses. Now, how do we do this in practice? Well, in practice, the way we do this is we make something called a color magnitude diagram. I have one plotted here on the right for you to look at. All right, so what's a color magnitude diagram? Well, a color magnitude diagram you make by looking at stars in the sky through two different filters. In this case, say, a red filter and a blue filter. And on the y-axis, you put how bright the star is in one of the filters. And on the x-axis, you put the difference between the two filters. And so in this plot, as you go to the right, things are getting redder, left is bluer. As you go up, they're getting brighter. All right, now, note that to measure the brightness, you actually need to know the distance. So you need to know the distances to stars. Fortunately, we have this satellite called Gaia that has given us distances to millions of stars. And so these are points from Gaia. Now, along in this space of color versus magnitude, main sequence stars, stars that are in the main part of their lifetime, form, well, a sequence. That's what's shown here. Each of these dots is a single star. Objects that are too far from the track aren't stars or aren't main sequence stars. They can be stars in another phase of their evolution, or they could be background objects like quasars or distant galaxies. By looking at where stars are along this sequence, we figure out how many stars there are, and we can then figure out their masses, because it turns out what determines where a star falls along this sequence is basically just its mass. All right, so that's what I've illustrated here. Each of these sort of boxes corresponds to a different range of mass. Starting at the bottom, box 1 is from 0.1 to 0.145 solar masses. box 2 is 0.145 to 0.19, and so forth up until the last box, which goes up to 1 solar mass. So you do something very, very simple. You count how many dots there are in each box. And when you do that, you get something like the IMF. All right, so what does that look like? Well, here's a count of the number of stars in each box. So the x-axis is the mass, and this is on a logarithmic scale. So -1 here corresponds to 1/10 of the mass of the sun. 0 corresponds to the mass of the sun. And the dots are just how many points there are in each box. The different colors are showing different models that can be used to draw where the boxes are. All right, so that's the biggest uncertainty here, is converting the light to mass. There is some uncertainty there. And that's what these different colors represent. Nonetheless, you can see that there's this fairly clear pattern of just counting number of stars in each unit of mass. That's the IMF. Now, you can immediately see from this plot, the sun is actually a little more massive than usual. The peak of this plot is here at something like 1/10 or 2/10 of the solar mass. So the sun is a little more massive than the average star. Not hugely so, but it's a bit more massive than the average star. Now, that only works up to about the mass of the sun. And the reason, as I mentioned, is that if you go to older stars, well, they've changed their masses, or they've disappeared, or excuse me, more massive stars, they've changed their masses, or they've disappeared completely. So how do we measure the IMF for more massive stars? The answer is we look at star clusters, like the Orion Nebula cluster here. All right, so we can't just look at stars near the sun to measure the IMF at higher masses, because we can't assume that the present day mass is equal to the initial mass. A second problem, which I haven't mentioned before, but I'll mention now, is that for things that are much less than about 1/10 of the solar mass, we can actually only find them, for the most part, when they are young, because when they get older, they get very, very dim and hard to see. So if you can find them, you can measure their masses, but you can't find them. So the solution is to look at star clusters. All right, so if you look at star clusters, you can measure the IMF in young clusters, clusters that are young enough that no stars have lost any mass, and brown dwarfs are bright enough that you can actually see them. Right now, there's some challenges too. The statistics are significantly worse, and because there are just fewer stars, you have to worry about dust. You can see the dust lighting up in this picture. It's harder to determine mass from light when the stars are young, but this is the best available method. All right, now I'm seeing a question, which is, how does star formation rate vary with star-forming cloud mass? And are they mutually dependent? That is an excellent question, the answer to which is we don't exactly know, and that is still debated, but the IMF does not appear to vary much by cloud mass, and I'll talk about that in a moment. All right, so here's the IMF in star clusters. What do we get if we do this exercise? So here are IMFs measured in a bunch of star clusters. So if we focus on the left-hand panel here, these are young clusters. For comparison, the right-hand panel is older populations. And you see the older populations are generally missing the more massive stars because they've disappeared. All right, and what you see is that all of these star clusters have rather similar IMFs. I mean, they're clearly not identical, but they all are qualitatively very similar. And in particular, they all have this distinct shape of a peak somewhere in the vicinity of about 2 solar masses, a broad plateau, and then a fall off at higher mass. All right, so there's another question here. Can't we model the initial mass by taking the present mass and adding the lost mass by making a physical model? That's an excellent question. For the stars that still survive, we can attempt to do that. But in many cases, the star isn't there anymore. If the star has died in a supernova explosion, then the mass that has been lost is all of it, or almost all of it. And the neutron star that's left behind, we often can't find or see. And so that's impossible to correct for. If the star has just lost a little bit of mass, we can try and correct for it. But if the star has exploded as a supernova, there's not much we can do. All right, so if we go back to this plot, we see that all of these regions, whose names I've put down here, they go by such charismatic names as the Chameleon, IC348, and Lambda Orionis, Rho Ophiuchus, and lots of Greek names. ONC is the Orion Nebula cluster. It's that one I showed you before. All right, now, the interesting thing is these are all pretty much the same, and they agree pretty well with what you get from just counting up stars in the solar neighborhood. That's the dotted line. All right, so all of these IMFs look pretty similar, and this is at least somewhat surprising, because the clusters that I'm showing here are wildly varying in their physical properties. So let me just try and drive that home by showing you some pictures of some of these clusters. All right, here's one. Here's IC348. That's one of the ones I plotted. All right, here's what it looks like, and I put in a scale bar there showing you 1 parsec or 3.26 light years on this image. All right, so this is a cluster of about 300 stars. Now, for scale, let me put that next to the Orion Nebula cluster. Here's the Orion Nebula cluster. Every one of those X's or circles is a star. All right, this image I've chosen because then you can see exactly how many stars there are and how dense they get. All right, so the Orion Nebula cluster has a factor of 10 more. It's about 3,000 stars, and you can see that physically it's just much bigger. All right, so here's the Orion Nebula cluster. Now for scale, the Orion Nebula cluster is a sort of medium-sized cluster. Let me put another one with the same IMF on. This is the cluster R136. And again, look at the scale bars here. Here's how big IC348 is compared to it. Here's the Orion Nebula cluster compared to it. All right, this is about 1 million stars. Now, the remarkable thing is that despite the immense difference in the sizes of these star clusters, the IMF is basically the same. Peaks in the same place, looks very similar. All right, so that's at least somewhat surprising. Now we have a question, can we get information on the slope of the IMF from simulations? And yes, I will talk about that. I promise to get to the simulations. That's what I'm going to talk about in the second half of the talk. All right, so this is at least a little bit surprising. The IMF, in all of these regions that span this huge range of size and mass and other properties, looks to be the same. So the bottom line is, the universe seems to like to make stars at a particular mass, which is about 20% of the mass of the sun. Why? This is a fundamental mystery in astronomy. Why do stars have that mass? Why isn't the typical star vastly larger than the sun, vastly smaller? It turns out the typical star is, 1/5 the mass of the sun. Why does the universe like that number? It's like we went out in geology and measured mountains, and we found that all mountains have about the same height. Why? It's got to be telling us something fundamental. Now, I should mention that this is an old problem. Old meaning going back at least a century. And so I have some evidence of this, and you can, I should mention that for any of you who've ever looked at astronomy and done astronomy work, you can find all of the papers I'm about to show on the NASA astrophysics data system. They've scanned them all going back to the early 20th century. So you can actually find all of these online. So this question, what sets the masses of stars? One of the earliest mentions I can find of it is in this Beckerian lecture given by Arthur Eddington in 1926. And it's well worth looking this up and reading it just because Eddington's a really smart guy. So this is the 1920s. No one has built a radio telescope yet. Nuclear energy is not really understood. And in this lecture, which Eddington delivers, he successfully deduces all sorts of things about interstellar space, just by being really smart. And one of the things that Eddington discusses is that, well, stars probably form out of the matter and the mass in interstellar space. And so you'd like to be able to understand where their masses come from. So in this lecture, he poses some questions and suggests some answers. The funny thing is that this letter drew a response. So this was published in a journal called The Observatory, and it drew a response from James Jeans. And it's worth taking a moment to read his comment if you can. I'll read it out loud. So much work has been done on isothermal equilibrium that it is difficult to understand how Professor Eddington can harbor the illusion that he is doing pioneer work in unexplored territory. yet his complete absence of reference to other theoretical workers suggests that such is actually the case. So this is a letter complaining about not being cited from James Jeans. So the thing that makes this particularly hilarious, which I have to mention, is that at the time this letter was written, so these two guys are trading letters in this, open letters in this journal, Eddington and Jeans were both professors at Cambridge. Their offices were about 1 kilometer apart. It's just that they really hated each other and wouldn't talk in person. So instead, they just exchanged these snippy letters. It goes on. Gentlemen, in your August number, Dr. Jeans deals rather severely with a portion of my Beckerian lecture. I would point out that the last half of his letter is occupied with an entire misunderstanding. And it goes on. It keeps going. I've stopped at 4 letters. May I conclude by assuring Professor Eddington it would give me great pleasure if he could remove a long-standing source of friction between us by abstaining in future from making wild attacks upon my work, which he cannot substantiate. I think the best part of this, in some ways, is the wonderful Edwardian English language. These guys clearly hated each other, but it's written in this very, if the learned gentleman would only remove his head from his own hindquarters, he would see. Now, I put this up in part because it's funny to see these two famous physicists and astronomers sniping at each other this way. But I also put it up because there's actually something significant here. So if I go back 1 slide and show you the third of these letters. So Eddington writing to Jeans, I had long admired this ingenious paper. He's referring to a paper where Jeans introduces something called the Jeans instability, which some of you may have heard of. It's a phenomenon whereby if I have a uniform density gas, but its size is too big or its mass is too large and I perturb it, it is unstable to gravitational fragmentation. It's unstable to the small perturbations growing and gathering more mass via gravity and fragmenting to collapse. And Jeans had proposed the idea that this instability is what's responsible for setting the masses of stars. You can get a mass scale out of this. Now, Eddington has a very, very clever response here. He says, I had long admired this ingenious paper, but having come to the conclusion that the masses of stars are determined by radiation pressure independently of the primitive density, I ceased to accept it. Now, this is an interesting observation that Eddington's making here. So Eddington is pointing out that the masses of stars are not random. They are a very, very special mass. All right, and in his book, he's a wonderful lay science writer. He posits the following question. He says, suppose that we construct spheres of gas of differing mass, and suppose that we go from one that is 10 to the 27 kilograms, 10 to the 28, 10 to the 29, 10 to the 30, and we just number them. What we will find is that all of the ones up to number 31 or 32, about the mass of the sun, are rather boring and are completely dominated by gas pressure. All of the ones after number 34 or so are completely boring and are totally dominated by radiation pressure. In between, you have a regime where radiation pressure and gas pressure are about comparable. It can't be a coincidence that the masses of stars live right at this crossover regime. That's Eddington's argument, and it's a very clever one. Now, today we don't think that radiation pressure is quite the key, but something similar and related will come up later. So just keep that in mind. So, all right, we want to understand why stars have the masses they do. Let's talk a little bit about what physics could be responsible for setting the masses of stars. So let's start with the basics. Stars form when interstellar gas clouds collapse under their own gravity. All right, so if we look at our galaxy, we can make a map of these clouds. Here are a bunch of clouds found near the plane of the galaxy, which have a total mass of about 1 billion times the mass of the sun, 10 to the 9 solar masses. And these clouds are mostly composed of molecular hydrogen in the form of the H2 molecule, with trace amounts of the carbon monoxide molecule. And that's actually the thing we're looking at here. This map that I'm showing you is a map of radio emission from carbon monoxide. So this is what we see for star formation. Now, these clouds are very dusty and are opaque to starlight. So these are the environments where stars form. Now, what are the properties of these clouds where stars are forming? Well, first of all, the gas is cold. All right, so what do I mean by cold? I mean, typically temperatures are around 10 Kelvin. So not much above absolute zero and only a little bit warmer than the cosmic microwave background. So why is the gas so cold? Well, the basic reason is that the thing that heats up interstellar gas is starlight, and these clouds are dusty and opaque, so starlight can't get in. So what does set the temperature? Well, it turns out the one thing that can get in is cosmic rays, relativistic particles that are accelerated by supernova explosions. They fly into these clouds, hit the H2 molecules, and produce fast electrons that then thermalize and share their energy, and that's how the clouds get heated. Now, how do they cool? Well, the cooling is because H2 molecules run into CO molecules, which then get excited. The excited CO molecules then radiate away energy. So there's a question, how did the dusty regions form in space? All right, that's an excellent question. The answer is the dust was made by stars. So stars produce heavy elements, and some of those heavy elements are collected into dust grains. So that's where the dust comes from, is it comes from a previous generation of star formation. So if I go back to this balance of heating and cooling is what determines this temperature of 10 Kelvin. Now, that's one factor about clouds. The second factor is that they're magnetized. All right, and the reason is these cosmic rays produce free electrons. And anytime you have free electrons, you have the ability to carry a current. So this gas is a plasma. It's not a very good plasma. Only about 1 electron in a million is free. But it turns out that 1 free electron per a million is plenty to carry all the current you need to maintain a magnetic field. So this gas will be magnetized. All right. This balance of heating and cooling is achieved very, very fast. So it takes about 1,000 years compared to about 1 million years for the gas to move anywhere, which means the gas is approximately isothermal. The gas is moving around much faster than its sound speed. So star-forming clouds are basically described by supersonic magnetized isothermal turbines. All right, and I'm seeing a couple more questions. So were stars formed first, or were the gas clouds formed first? Well, the first stars formed out of gas clouds that didn't look like this. The first stars formed out of gas clouds that didn't have any dust or carbon monoxide. That is an interesting question, exactly how and under what circumstances. It is an entirely separate lecture, which I'm not going to skip over in this one. That is an excellent question, just not one for this lecture. All right, other questions. Do passive galaxies have a star-forming history? Well, if they were ever star-forming, they did. Passive means they're no longer forming stars. And then finally, why is CO the one responsible for cooling with fast electrons also radiate? Good question. So the fast electrons do lose some of their energy by radiation. We don't tend to count that as cooling because that energy is not coming out of the budget of the thermal energy of the gas. We tend to count that as just there being less heating from the fast electrons. So when we talk about cooling, what we usually mean is that the thermal reservoir of the gas is losing energy, and the fast electrons are not part of that thermal reservoir. So that's why we don't tend to count it as the cooling. For getting energy out of the thermal reservoir of the gas, that has to be CO. All right, I think I'm going to stop taking questions for the moment because we're sort of running out of time. So I'm going to go on from now, and I'll answer more questions at the end. So here's what these clouds actually look like if you zoom in on. All right. The point is they're a god-awful mess, right? That's what you should be seeing in this picture. They look like, you can see that they're sort of striated. The striations are probably coming from magnetic field lines. They look incredibly complex. But beneath this complexity, there's a simplicity, which tells us something about where stars get their mass. So here's the problem. Isothermal, meaning constant temperature turbulence, is scale-free. And it can't possibly explain why the IMF has a favored mass, why the universe likes to make stars at a certain mass. All right, so here's a mathematical demonstration. So this is like the one equation in this talk. And I put it in here because even though the equations are horrible, the conclusion to draw from them is extremely simple. So here are the equations describing self-gravitating magnetized isothermal turbulence. Rho here is the density, T is time, V is the velocity, CS is the constant sound speed, phi is the gravitational potential, B is the magnetic field. I don't expect you to follow all these equations. The point is the following. These are the equations that describe the system I've just talked about. And what we can do is we can just do a trick called non-dimensionalizing. So what I'm going to do is I'm going to just divide all the densities by some average density rho naught. I'm going to divide all the magnetic fields by some average magnetic field B naught. I'm going to divide all the velocities by the sound speed. And I'm just going to do an arithmetic transformation on these equations. So here are the same equations written in non-dimensional form. So R here is rho over rho naught, U is velocity divided by sound speed, etc. Same equations. Now, here's the reason to non-dimensionalize equations like this. Some numbers come out of this. This n is the Mach number. It tells us about how fast the flow is compared to the sound speed. This Na is the Alfvén Mach number. It tells us how fast the flow is compared to Alfvén waves, which are the magnetic equivalent of sound waves. It tells us about this alpha Vir is the virial parameter. It tells us about how strong gravity is. These three numbers determine everything. If you know these three numbers, you know the solution to these equations. Now here's the problem. These dimensionless numbers are obviously unchanged if I just do the following. Multiply the density by some number x, multiply the length scale by x to the minus a half, multiply the magnetic field by x to the minus a half. If you do that and you plug into these three formulas, you'll find these dimensionless numbers stay exactly the same. But the mass of everything, well, that depends like on density times length cubed, changes when I do that. The implication of this is that these equations are not capable of identifying a preferred mass for stars. These equations by themselves, just from this dimensional analysis, I can prove can't set a mass for stars. And I can demonstrate that numerically. So here, if you don't believe my math, here are some computer simulations done by a PhD student working with me, David Gusenyov. And what we did in these simulations is we let a gas cloud collapse under gravity. And all we did is we increased the resolution of the simulation. So each of these colored lines just represents a different, identical simulation, but where we increase the resolution. And as we increase the resolution, you see that the characteristic mass, the most common mass formed for a particle in these simulations, just gets smaller and smaller and smaller. Now, these simulations do, of course, have a mass scale in them. That is, we can only do the simulation at finite resolution. Our computer budget is not infinity. We ran this on a computer that has a finite amount of processing power and memory, and so we have to have a smallest particle in the simulation. And it turns out the characteristic mass we get is just determined by the mass of that smallest particle. Other than that, it just goes to smaller and smaller masses as we increase the resolution. So just from dimensional analysis, we've learned we have a problem. So what does explain the IMF peak? It has to involve a deviation from this idea of isothermality. So how do we do that? How do we understand that? Well, the gas in a molecular cloud, it turns out, ceases to be isothermal once it gets dense enough. And the reason is what's keeping it isothermal is radiation from carbon monoxide and then later on from dust grains that are mixed with the gas. But there's a fundamental law of physics. That fundamental law says that nothing can radiate more efficiently than a black body. All right, a black body is the most efficient possible radiator. That is a corollary of the second law of thermodynamics. So you can imagine a collapsing blob of gas, and as it's collapsing, it's trying to radiate away its cooling energy. Right? Every time it decreases by a factor of 2 in radius, its gravitational potential energy gets a factor of 2 larger. If it's going to stay the same temperature, that energy can't go into heat, it has to be radiated away. So every time the density doubles, I need to get rid of that energy as radiation. And once the thing is too small, once the object reaches a small enough size, I can't do that because in order to get rid of that energy, I would need to radiate faster than a black body. At that point, the thing has to start heating up and stop being isothermal and stop collapsing. And it turns out that the mass at which that happens is of order 1/100th of the solar mass. Now, once that happens, the mass that's falling onto that initially collapsed 1/100th of the solar mass, hits its surface and shocks and heats up. And that heat is then carried outward, warming up the surrounding dust and gas. So that's the cartoon here. Every star that's forming, every one of these little 0.01 solar mass seeds, winds up with a little island of warm gas around itself. Now, this is interesting because that warm gas can't fragment any further. It's too hot. Pressure is raised when the temperature is raised, and the pressure in this little island is high enough that it is stabilized against breaking up into small pieces, little pieces. Gravity can't gather them together because the pressure is too large. So the size of this island sets a limit on the masses of stars. Now, how big is each island? Well, the little star in the center is 0.01 solar masses, but the island is more than that. There's more mass around it. What determines the size of one of these islands? Well, approximately what determines the size of the warm island is the escape speed from the surface of the star. Because the mass is falling onto the surface, the faster it falls, the more energy it liberates when it hits. And the more energy it liberates, the more I can heat up. So the escape speed that determines how fast the stuff is falling when it falls, when it lands, that's what determines how much energy I have available. Now, what sets the escape speed from the surface of a protostar? And here is where we get back to Eddington's answer and some nuclear physics. And we explain where the universality of the IMF comes from. So it's a curious fact about stars. All main sequence stars have roughly the same surface escape speed. Not exactly, but it doesn't vary by that much. Why is that? Well, it turns out the surface escape speed of a star is directly linked to its central temperature. The higher the central temperature, the higher the surface escape speed. And it turns out that all main sequence stars have pretty comparable central temperatures. Varies by a factor of a few, but not much more than that. Why? Because of nuclear physics. Because stars work by burning hydrogen into helium. And the rate at which hydrogen is burned into helium is incredibly sensitive to temperature. So a small variation in temperature results in a huge variation in the rate of burning, and stars stabilize at a certain central temperature. The center of our sun is at about 10 million Kelvin. Well, it turns out that protostars are similar, except that what sets their central temperatures is not hydrogen, but deuterium. The Big Bang created deuterium as well as hydrogen. And deuterium burns at a temperature of about 10 to the 6 Kelvin, about 1 million Kelvin. That's what sets the surface escape speed from protostars. And that is what sets ultimately the sizes of these warm islands. So can we do a simulation to actually test if this works? The answer is yes. So here is a simulation. On the left side, I'm showing you density. On the right side, I'm showing you temperature. And you can see the warm islands forming around these stars as they collapse. All right, so I'll let you watch that a couple more times. You see a turbulent gas cloud collapsing and forming stars, and as it does so, the gas heats up and I form these little warm islands that they're packed so closely that you can't really distinguish the individual islands once many stars form. But if you look at the beginning of the movie, you can see the little islands forming around the individual stars. And this process sets the masses of stars. So we can check in this simulation, how does this compare to what we actually observe for the stellar mass distribution of the IMF? And that's what I'm showing here. So just to orient you in this plot, the x-axis is stellar mass measured in solar masses, and the y-axis is what fraction of the total stellar mass is contained in stars less than the value on the x-axis. So the way to read this is, if the x-axis value is 1 and the y-axis value is, say, 0.2, that means 20% of the mass is found in stars that are smaller than 1 solar mass. So the green line is the simulation, and it's moving because it's showing what happens as the simulation runs. The gray band is showing what you get if you take the observed initial mass function of stars and just pick a mass equal to the mass in the simulation. And you see that the green line is staying within the gray band. They're statistically compatible. And you can zoom in and confirm that this is actually what's happening. So the nice thing about simulations is that we can actually, we have the full thing in the computer. We can go back to the point where every single star forms and ask, what's going on around it? What's the density and temperature distribution around it? So here in this simulation are just some sample stars. I've got 8 stars chosen here just randomly to form in the simulation. And I'm showing you the density field and the magnetic field around the point where each of them collapses. And around each one, I can draw circles, concentric circles, and ask, what does the temperature look like? So here's just an example of one of them. So here is what the temperature is doing around it. You see that I get far away. The temperature is going back down to this background of 10 Kelvin, but near the center, near this protostar, the gas has been heated up to 40 Kelvin. Here's what the density is doing. Here's the magnetic field. And you can ask, well, does this hypothesis hold? Is the mass of the star being set by heating? And that's what this bottom panel is showing. So the black line is just as I draw bigger and bigger concentric spheres, how much mass is contained within each of them. The blue line is showing how much mass can be supported by the thermal pressure. And you see that these two cross at, lo and behold, about 0.2 solar masses. That's the typical mass of a warm island, and that's what holds the clouds up. So that's what sets the masses of stars. We're almost at the end. Here's my summary. So the universe likes to make stars with masses of 0.2 solar masses. It's a fundamental fact of nature. And this requires a deviation from the isothermal behavior that mostly prevails inside star-forming clouds. The most likely explanation is the warm islands created when seed stars that form at masses of 1/100th of solar mass heat up the gas around themselves. That's where the 0.2 solar mass comes from, is that this 1/100th of a solar mass little seed has an island of 0.2 solar masses around it. The masses of these islands are determined by the star's surface escape speeds, which in turn are set by nuclear physics. And this explains the near universality of the IMF. This explains why the typical mass is the same everywhere, because it's being set by nuclear physics. And nuclear physics is not different inside IC 348 or the Orion Nebula Cluster or R136. Nuclear physics is nuclear physics. That is why the IMF is universal. But, yeah, there has to be a but. The research can't end. So here's the but. The emerging challenge is going to more distant galaxies. Now, the most direct way to measure the IMF is to count individual stars. But we can really only do that in the Milky Way and a few nearby galaxies. You go further than a few megaparsecs away, and you just can't make out individual stars anymore, particularly not low-mass ones. They just are too close together, they become confused. And even with Hubble Space Telescope, you can't separate them. So you can't count individual stars anymore. However, you can still measure facets of the IMF from integrated light. And what I mean by that is I can't separate out the light of the individual stars, but I can measure the light of all the stars together. And you can look for features in the spectrum that correlate with the properties of particular stellar masses. All right, so here's an example from this paper by Van Dokken and Conroy. So if you look at the top panel, what they're showing is a very small range in wavelength, around 0.82 microns. And they're showing stars of different spectral types. And what you'll notice is that dwarf stars, M dwarfs, have this absorption feature called Na1, sodium 1, which the other types of stars don't. Now, the interesting thing is that the stars that are M dwarfs are a pretty narrow range of mass, about 0.1 to 0.15 or 0.2 solar masses. So the depth of this feature relative to the background is telling you how common stars in that mass range are. Now, here's the interesting thing. If we zoom in, what they find is that So the sort of standard IMF would be something like that we see from star counts would be something like the purple or the green line. The observations seem to favor something a little deeper there, which suggests that the characteristic stellar mass is maybe a little lower. So 0.1 solar mass stars are more common than 0.2 solar mass stars in this galaxy. Now, this is preliminary. There are still ways this could be wrong, but it's interesting, and it suggests that we haven't told the full story of the IMF yet. I think I will end there and answer any remaining questions. So thank you all for your attention. I will stop sharing my screen. All right, and I will take questions. All right, so we already have some in the chat. So let's see. This one, I think I already answered, so I'll skip it. So process of the birth of a star in a white hole. I'm not quite sure what a white hole is in this context, so I don't think I can answer that. Does star formation affect galaxy evolution? Absolutely, by a lot. I mentioned that the dominant source of feedback that affects galaxy evolution is supernova explosions. And the stars that explode as supernovae have very short lifetimes on galactic scales. They blow up as supernovae within a few million years to a few 10 million years of forming, which is very short on the lifespan of a galaxy. A galaxy like the Milky Way takes 200 million years to make one orbit. So star formation is immediately followed by a bunch of explosions. And this is a very strong effect on the formation of galaxies, on the evolution of galaxies. So the gas from supernovae sometimes recycles back to form stars. Does this play an important role in the temperature balance? In a way, yes. So by the time the gas is getting back to forming stars, all of the thermal energy from the supernovae is gone. It's cooled back down. So the supernova has been forgotten in that sense. The way in which it hasn't been forgotten is that supernovae produce not only heat, but heavier elements. So I mentioned dust, I mentioned carbon monoxide, et cetera. All of these things are made by supernovae. So supernova explosions are what's responsible for all of that stuff. So the fact that we've had supernovae producing those heavy elements is important for how the gas behaves. I, in fact, have a PhD student right now who's looking at how we go from the primordial star formation case where we don't have any of those heavy elements to a modern star formation regime which is dominated by those heavy elements. All right, why hydrogen and helium formed during the birth of the star? So it's not that hydrogen and helium formed during the birth of the star. Hydrogen and helium were made by the Big Bang. So when you form the first stars, those are the only things around. It's only later on that stars start to make elements heavier than hydrogen and helium. How do we calculate the density of these molecular clouds? That is an excellent question. It's tricky. How do you calculate the density of something that you only see in projection? There are a couple of techniques that people use. So one is to exploit the fact that different molecules light up at different densities. So there's something called the critical density of a molecule, where if the density of things that are colliding with that molecule is low, it doesn't light up very much. And there's a density at which it lights up maximally called the critical density. By using different molecules with different critical densities, we can get an estimate of what the density in regions where those molecules are emitting is. That's one method. It's not the only one, but that's probably the most direct. All right. Will all protostars have to accrete the same amount of matter? Accretion can depend on various factors. That is absolutely right. And not all protostars do accrete the same amount of matter because not all stars wind up at the same mass. So I showed you that, in that simulation, the flow is extremely chaotic. And so you wind up with a wide range of masses. So in this talk, I just focused on what's the typical mass. But in fact, in that simulation, we form a range of masses. And you can try and make theoretical models for not just what is the mean mass, but what is the shape of the distribution of masses based on the statistics of supersonic turbulence. And people have attempted to do that, including me. I just did not go over that in this talk. All right, regarding future prospects, how can artificial intelligence and machine learning help here? So, there are a number of places, but one that I think is intriguing is I showed you again that this flow is very, very turbulent, and turbulence is a huge unsolved problem in physics. And it's something where we've got some sort of empirical rules about how things behave, but conceivably those rules could be improved by artificial intelligence and machine learning. If we don't have a full physical theory of turbulence, maybe we can have at least a predictive model for how turbulence in different regimes behaves and what it does that we could embed in our simulations. And so that's something where conceivably there would be places for artificial intelligence to be helpful. So using this theory, can we predict the observed spread in the IMF? That's very closely related to the question I answered before. Based on what I talked about just in the talk, no. You can do more general things and try and predict the spread. And so David Gusenyov has done some things like that, working with me and his other supervisor, Phil Hopkins, where we've attempted to actually reproduce the full distribution and not just the mean from the combination of this heating effect and the statistics of turbulence. All right, if CO is present in trace amounts, how is it enough to cool the gas? It's a good question. The answer is it doesn't take that much. It is only in trace amounts. It's sort of 1 particle in 10 to the 4. But it turns out that it's still pretty effective at cooling, because even if only 1 part in 10 to the 4 of the atoms is a CO molecule, hydrogen atoms still hit them very, very often. Every time they do, there's a reasonable chance that some energy is going to be lost. So it doesn't take a very large quantity to get quite effective coolant. Can I suggest some good readings for stellar physics for beginners? Well, it depends on what you mean by beginner. If by beginner you mean you have a background in physics, but you haven't done any astro yet. So I teach a course, or I have taught a course on stellar structure, and I use the textbook by Prialnik. I find that that's a quite good textbook that has good sort of general physics. If you're looking for a more general introduction to astronomy, you haven't had really any astro background, but you have some, first-year physics background level. The book we use for our second-year astronomy course here at ANU is Astrophysics in a Nutshell by Dan Maus, and I like that one a lot. So that's the book we use for our second-year course. For our third-year course on stars, we use Prialnik. All right, let's see. So from the last point I mentioned, different galaxies might favor different mass stars. Does this mean some kind of new physics should be looked into? Good question. I think the answer is we don't know yet. So yes, there does seem to be some evidence, and I should say the evidence, the galaxies that show this are the densest and most extreme in the universe. We see this only in the cores of giant elliptical galaxies. And even then, it's not a big change in the IMF. We're talking about, instead of the most typical mass being 0.2 solar masses, it maybe changes to a little less than 0.1, right? So we're talking about, we go to the most extreme star-forming environment in the universe, it changed by a factor of 2 or 3. What causes that? That is still, I think, an open question. Does it require physics beyond what I've talked about? Not totally clear. So I think the answer is we don't know yet. All right, what is the role of quasars in the formation of galaxy? So quasars are the black holes at the centers of galaxies. They are the things that are accreting and lighting up as mass falls into the central supermassive black hole. They are probably in some ways associated with galaxies turning off. So what we observed is that as you go to more and more massive galaxies, you cross a threshold where the galaxies cease to have gas in star formation. So galaxies less massive than the Milky Way are all rich in gas. They form stars. The Milky Way is right on the cusp. And you go to things that are 3 or 4 times the mass of the Milky Way, they are mostly devoid of gas and aren't forming any stars. Now, interestingly, quasars are found predominantly in those more massive galaxies. And so our hypothesis is that somehow the quasar turning on is associated with the galaxy ceasing to have gas in star formation. Now, exactly what pathway that takes is still very much an open question. It might be that the quasar just ejects mass directly to the galaxy, but equally likely, in fact, I'd say probably more likely given the available evidence, is that somehow the action of the quasar prevents new gas from getting onto the galaxy. And then the gas that's in the galaxy gets consumed and turned into stars. But if you've got no new supply of gas coming into the galaxy, it goes dead. So that is probably the role of quasars, but that is still an open research question. All right, so do these simulations predict the IMF of POP3 stars? So population 3 stars, for those who don't know the terminology, are stars that are formed without the presence of any metals, the primordial stars. So the simulations I showed you weren't done for primordial conditions. There are other simulations that people in my research group have done that do mimic primordial conditions, and where the IMF that's produced is quite different. The simulations I showed here were for present-day conditions and do not include a lot of the physical processes that are important for primordial conditions. And conversely, the simulations of primordial conditions generally don't include the physical processes that are important to present-day star formation, for example, the dust. See, does the composition of the clouds affect the simulations and results? So that's a good question. So I have done a little on this, but others have done more. So the answer is that if you vary the abundances of heavy elements, but you keep them mostly hydrogen and helium, but you vary the abundances of the trace heavy elements over the range from that we see in the local universe, say 1% of the abundances of heavy elements in the sun to a few times, it makes remarkably little difference, a lot less than you might have naively guessed. Now, it's a good question, why? And I can talk about that, but I think I won't in response to this question for reasons of brevity. But over that range, it doesn't seem to matter. Now, you go to less than 1% the abundance of heavy elements in the sun, you go to 1/1,000,000th the abundance of heavy elements in the sun, yeah, I'm sure it does make a difference. You go to 0 heavy elements, you get primordial star formation where the IMF is very, very different. And so mapping out that regime is still actually very much a work in progress. That is, I mentioned I have a student who's working on a paper, he's doing exactly that. All right. So we know that gravity is actually curving of space and time around massive objects. So how did star formation happen from clouds of gas? They're not so massive enough for them to coalesce. I'm not quite sure how to interpret this question. I mean, I guess what I would say is that the gravity in the systems we're simulating is all in what in general relativity we call the weak gravity regime. We're in the regime where Newtonian gravity is an excellent approximation just because nothing is that dense, right? Even a star is very non-dense compared to a black hole. So general relativistic effects are basically not important for us. We in fact just use Newtonian gravity because the difference between Newtonian gravity and general relativity for the systems we're simulating is so tiny that it is not worth worrying about in comparison to like the round off error of a computer simulation, smaller than that. So why is it so peculiar for CO to be present? Why not any other gas? So the answer is there are other molecules present. Now, the reason I mentioned CO is because it's one of the most abundant past hydrogen and helium. So if you look at the elements that the universe consists of, hydrogen is the most abundant, helium is the second most, and it turns out that in the present-day universe, the third most abundant is oxygen. The reason is stars make a lot of oxygen. Carbon is also quite abundant, and then you get up to things like iron. But carbon, nitrogen, and oxygen are the most abundant elements other than hydrogen and helium this side of iron. And so what molecules do you wind up making a lot of? Well, molecules that you can make out of those elements. What's the simplest molecule you can make out of those elements? CO. So that's why I emphasize CO is it is much more abundant than any other trace element. But you do in fact see other things. You see ammonia and H3. You see other compounds made of carbon and nitrogen and oxygen, and sometimes other small, rarer elements like sulfur. It's just that CO is the most abundant because C and O are the two most abundant atoms after hydrogen and helium. Does gravity from neighboring stars cause any effect on the IMF of new or forming stars? So that's a good question. So are tidal forces from neighboring stars significant? Probably depends at least a little bit on the density of the region. And this is maybe one of the things that varies when you go to very, very dense regions is that gravity from neighboring stars becomes significant. In star-forming regions that we see in the Milky Way, generally, no. The tidal forces are not that important just because the stars are too far apart. But possibly in other galaxies where conditions are denser, it does matter. Why do stars vary in mass within the same cluster? Well, I can ask you to think about that movie I showed. The flow is highly chaotic, and not all the stars wind up grabbing the same amount of mass. Some wind up in denser regions where there's more mass around to fall onto them. Some wind up getting thrown out into the periphery where there's not much mass. And it's this randomness that generates the spread in the masses of stars. Could you tell something about the gene's mass and how it is related to star formation from clouds of gas? So, all right, so the gene's mass is something that emerges from a mathematical question or mathematical calculation. Calculation is done by genes, and it's the following. Suppose that I have a ball of isothermal gas, and what I'd like to do is I'd like to perturb it by putting some sound waves in it. Now, if gravity is not an important force, I know what sound waves do. I perturb the gas and I just get a propagating sound wave that moves away. And that's a good description of how things work inside the Earth's atmosphere. In the Earth's atmosphere, the self-gravity of the air is not an important force. But you can imagine I take a bigger and bigger medium. Let me take not the Earth's atmosphere, but something with the same density as the Earth's atmosphere, but extending out to the orbit of Jupiter. Well, now I can no longer ignore gravity. So there's a critical size beyond which this sound wave, rather than oscillating and going back and forth like this, well, when it starts to compress, the pressure won't be enough to make it re-expand against the force of gravity, which makes it want to compress further. That size scale is called the gene's length. It's the critical length at which sound waves no longer bounce back, they instead collapse because of gravity. And if you take the gene's length and you cube it, and you multiply by the density, you get the gene's mass. It's the typical mass of a self-gravitating object. The way you can think about it is that things that are masses that are smaller than a gene's mass can't gravitationally collapse. Things that are bigger than a gene's mass can, and if there are any perturbations, they will tend to break up into things that are about a gene's mass. So that is probably, so that is related to the mass of stars in the sense that the characteristic mass of stars is about a gene's mass. Now, the trick is the gene's mass depends on the pressure, which depends, because that's what determines how strongly sound waves bounce back, and the pressure depends on the temperature. And what's setting that temperature is heating from stars. So the gene's mass is the characteristic mass of a star, but the key ingredient here is that you need to know the temperature to compute the gene's mass, and to calculate the temperature and the density, you need to know about this heating from stars. So were the properties of elements similar to that of elements on Earth? Well, I'm not quite sure what this question means. The chemical and physical properties of elements are the same everywhere. An atom is an atom, all right? A carbon atom in space is a carbon atom on Earth is a carbon atom. Atoms are atoms. What's different between Earth and space is the abundance of different atoms. The Earth is made mostly of iron, whereas gas in interstellar space is mostly hydrogen, helium with trace amounts of things, including iron. But the physical properties of an atom are just what they are. They don't care what the atom is. All right. Maybe if we include GR effects, we can attain a far better picture of what is going on. So when I say that we don't include GR effects, it's not that we're pretending general relativity doesn't exist. It's that I can calculate quite precisely how big the general relativistic correction anything I'm doing is. All right, so you can say, well, all right, I can calculate, say, the acceleration of these two bodies under Newtonian gravity, and I can calculate quite precisely under general relativity what would the acceleration be instead. And the answer is it would differ in the 15th or 16th decimal place. So when I say that we don't include GR, it's not that it's not that we're ignorant of GR. It's not that we don't understand how to include it. It's that we are confident because we've done the calculation that it doesn't actually matter for what we're doing. All right, in exactly the same way that, like, if I am interested in a problem in mechanics, I want to shoot an arrow into a target, and I want to figure out what angle to aim the bow. I don't worry about the relativistic correction, right? I do that calculation using Newtonian mechanics, and I don't worry about including the rest mass of the arrow and doing the special relativistic correction. Not because I don't know about it, but because it's in the 15th decimal place, so who cares? So do star formation conditions near the center of the galaxy give similar results? That is an excellent question. And the answer is sort of, it depends. It's not that simple. So it's a complicated question. The conditions near the center of the galaxy, there's a much stronger background radiation field. The gas is denser and more turbulent. I think the answer is we're not quite sure. So I think that the most honest answer is we don't know yet. All right. Is the abundance of CO tested by practical observations, or are we just guessing it based on the simplest possible molecule? Well, so yes, we observe the CO molecule. We know it's there because we see radio emission from it. All right, so every molecular atom has its resonant frequencies that it emits at. For CO, what we see are the rotational lines of CO. So you can think of CO quantum mechanically as a barbell, right? It's an oxygen atom and a carbon atom in a barbell. And quantum mechanically, for a two-atom system like this, the simplest, lowest energy excitation it can have is it can rotate. And that rotation is quantized. And so there's a particular frequency that we see for radiation emitted by CO molecules in the J=1 state going to the J=0 state. We see that coming from molecular clouds. That map I showed you of the molecular clouds is made, in fact, using that radial line. Now, if you look at a bunch of those lines, and you also look at not just CO, but its isotopologues, so carbon-12 with an oxygen-18 instead of an oxygen-16, or carbon-13 instead of 12, you can diagnose the abundance of CO pretty well. And yeah, so that's what our estimate of the abundance of CO is based on, is those observations of those lines. All right, I'm trying to get through the questions, but more keep coming. So I think I see 4 now, and I'm going to answer these 4. And then I think I'm going to have to stop because, you know, I need to go home and see my family. And it's getting late here. So could dark matter halos have any effect on the IMF of the population? So all of this is occurring inside a dark matter halo. So the way I think about it is the dark matter halo is providing the arena in which this whole game is being played out. But it's not so important on the scales of the IMF, and the reason is that, at least as far as we understand, the dark matter distribution is very, very uniform on the scales where star-forming clouds exist. So we're talking about scales of, I showed you those pictures of star clusters and, you know, a parsec, something like that. On scales of a parsec, the dark matter distribution is creamy, smooth peanut butter. There isn't really a structure, which means that it doesn't perturb anything or exert forces. It holds everything in place, but it doesn't exert significant forces. All right. Black holes radiate Hawking radiation at the center of the galaxy, which leads to the formation of stellar bodies. The answer is not really, because Hawking radiation is utterly tiny from the mass, from a black hole whose mass is like the mass of the black hole at the center of our galaxy. The amount of Hawking radiation coming out of that is truly tiny. Hawking radiation is significant for very small black holes, but for black holes the size of, you know, what we have in the center of the galaxy, or even a stellar mass black hole, it is so small that you would never notice it compared to the light that's coming just out of the stars. So it's just a small effect. How are elements beyond iron formed from stars? I mean, so yeah, that's a good question. So depends on the element. There are a couple of different pathways. So some are formed in what are called asymptotic giant branch stars, which are stars where you have a sort of an onion structure where you have a layer at the bottom, which is very neutron rich. Others are formed in mergers between neutron stars. In general, to get elements beyond iron, you need a very neutron rich environment. You need an environment where there are a lot of neutrons, and that sort of thing is formed in the bases of AGB stars or in neutron star mergers. That's where those elements come from. All right, last question. CO on Earth causes global warming, but it causes cooling in star formation. Is that correct? Well, so the global warming is mostly CO2 rather than CO. But fundamentally, yeah, I mean, it has to do, the fundamental physics here has to do with the fact that this molecule is capable of both emitting and absorbing light in the infrared part of the spectrum, and in in fact, even in the radio part of the spectrum. So on Earth, the greenhouse effect comes from the fact that the molecule doesn't absorb optical light, it doesn't absorb sunlight, but it does absorb infrared light. And so sunlight comes in and passes right through the atmosphere, hits the Earth's surface, is re-irradiated in infrared, and then gets trapped because this molecule absorbs it. In molecular clouds, the fundamental property is that if a molecule can absorb radiation at a certain wavelength, it can also emit that wavelength. And so what's going on in molecular clouds that's causing cooling is the molecules are getting excited by being hit by H2 molecules. So CO molecule, H2 molecule comes along, rams into it. The CO molecule gets excited and then emits radiation, which escapes. That's the cooling mechanism. So depending on the circumstances, molecules can be both heaters or coolers, depends on the environment and what's going on around. I think that was the last question.
Fantastic.
Thank you, everyone. I'm exhausted now.
Well, great. Thank you very much, Mark. That was a fascinating and interesting talk. Thank you also for taking all of those questions, all 37 of them. You've done very well. And thank you for all those who came and attended the talk. Thank you for asking those questions. I hope you all enjoyed, found the talk interesting. There's a lot of research groups over at Mount Stromlo Observatory, part of the Research School of Astronomy and Astrophysics. So I'm sure you can find them on the website. You can look at all the interesting stuff that's going on and all the research that's happening. If you're interested in joining, becoming part of the research or studying over there, please get in touch with us. And yes, we have about a dozen or so of more talks to come in this series. So if you haven't yet registered, please do. Otherwise, I'll see you at the next one.
Thank you, everyone. Bye.
Have a great rest of the day. Thanks once again, Mark. Take care.
Bye.
Goodbye.